Welcome to qnawire.
The first step is to figure out what the acceleration of the elevator is at 4 seconds. We're given that the velocity with respect to time is this expression here. And we know that the acceleration with respect to time is just equal to the derivative of the velocity with respect to time. And so taking the derivative of this, we get 3 plus 0.4 t, just by bringing down the 2 and then lowering the exponent by 1. And now, from this expression, we can figure out what the acceleration at 4 seconds is by just plugging in 4 for t. 4 times 0.4 is 1.6, plus 3 gives us 4.6, and this is in meters per second squared. Now, if we draw the force diagram of an object in an elevator, we have gravity pulling down, so it's mg. We have the normal force keeping us in the elevator and actually pushing us up to the higher levels, and that's just labeled by n. And we have an acceleration going up too. Now we know that the acceleration at 4 seconds is 4.6 meters per second squared, so that's what this is. But if we do Newton's second law on this in the y direction, we get the normal force minus mg is equal to the mass times the acceleration. I'm just going to leave it as a, but remember that we have actually solved for it at this point. The normal force is the force that you would read on your scale. And so it's what we actually want to solve for. It's equal to mass times acceleration plus mass times g, which is equal to mass times a plus g. Now plugging in 4.6 here and plugging in 9.8 for g, and plugging in our mass, which I believe in this problem is 76 kilograms, we get a normal force of 921.6 newtons, like that. And so this is what you would actually read on your scale if your scale is reading out newtons. And you could, of course, convert this into pounds. The point is that it would be higher than what he regularly weighs because there's an additional acceleration up, which is increasing the amount read off on the scale.